My name is James Lamar. I'll be discussing the NetworkMiner Graph Enhancement Project for Digital Forensics, Summer 2014. As an overview, the objective of this project is to analyze network traffic and support forensic analysis. The data is viewed at a macro level, presenting data as a network graph. It leverages two open source projects. NetworkMiner reads in PCAP files and processes that data, extracting relevant information. GraphSharp is a series of libraries which provides data structures and layout algorithms. The implementation is to take the data from NetworkMiner, transform it into a graph data structure that can be presented and laid out in a graphical format. It does this by extracting the nodes and metadata and putting connections between those nodes based on the packet traffic going back and forth, scaling the lines to represent the amount of traffic going between those nodes. So let's start by looking at a demo of the application. What you see here is essentially the binary distribution, some folders that NetworkMiner uses to store files, assemble files, and the project files, including some of the DLLs. The main application is NetworkMiner.exe. Running that application brings up the NetworkMiner GUI. Now there's already documentation on the website for this open source project on the basic operation of this model. The file menu has open, exit, and tools. Most important features are really being able to clear the GUI and delete the captured data, which can get fairly large for larger PCAP files. As you can see, there's different tabs, one for hosts, frames, images, etc. What's been added to this project is a network graph tab, and the beginning of some forensic analysis capability. Currently featured is the ability to put in a start and end time, select whether you want to see network traffic between that time interval or outside of that time interval, for instance, outside of normal operating hours. By hitting this checkbox, it will enable the ability of the program to filter out those packets. And it does that after you hit the Generate Graph button. So this button, essentially after you read in the PCAP file data, will open up a new window. And that new window will be the network graph. So we can look at some samples here. I'll start with a fairly simple example. This was from a CyberQuest challenge, and it really only has, as you can see, 3 nodes. And if I expand this, this will show some of the types of data that each node contains that we can also use to display in our network graph. So you have IP address, MAC address, hostname information if available, the operating system. This is done through some different fingerprinting codes, and then packets sent. So as you can see, this really just has one packet and shows the destination IP. So that destination IP would be another node, and the line width would go between these, representing one packet of data. So if we go to the Network Graph tab and generate a graph, you'll see a window comes up with 3 nodes. See the IP address, icon for the OS, the MAC address, what the OS is, and how many packets are transmitted and received. If I make this larger, you can see that the lines between the different nodes are different thicknesses, representing different amounts of data going between them. If I click over this, it will show in red how many packets are being received, relatively speaking, as well as how many are being transferred. And it will show this for every adjacent node. In this case, there's only one. So if I go here, you see It's connected to two nodes and you see both lines. Now as far as navigating, you can hold down the mouse button and move the graph around. There's a couple of other scaling features. You can use the slider to scale. You can go to a 1-to-1, or you could fill. At the top there's some different layout algorithms, 8 to be exact. And you can save the graph, you can load the graph, you could clear the graph. So those are all options, and you can generate multiple windows. So now let's look at a larger case. So I'm going to clear the GUI. With the captured files. Now I'm going to open up a larger case. So as you can see, it's processing the data, updating each of the tabs. In this case, we have more nodes than just 3. We have 16 in this case. If we go to the network graph, we can generate a graph. And as you can see, most of the data is going through this node as we go around, and this node. Now some of these boxes are a lot larger, and that has to do with they have a lot more host information, some domain name data, etc. And this one's a little bit more interesting to look at some of the algorithms. So there's a circular. You can look at various layouts here. Perhaps less interesting in this case is this tree structure. And this graph could be saved. So I could save this as test 1. Now I can clear it. And I could load that graph, test 1. And there's the graph. And I can manipulate it. As you can see, you can move the nodes. However, it doesn't save the node positions. Now, one of the other features is this filtering feature. So it turns out a lot of these transactions in terms of packets were done earlier in the morning. So if I put this, we just put it from 2 o'clock to the end of the day. Now if I generate a graph, it may not be totally obvious, but there's fewer connections, and they're not quite as thick. I can compare that to the graph I had before. You can see the connections, there's quite a bit more. Now if I put this much later, and generate a graph, now I show no connections because none of the packets were transferred during that time. You can also load some larger cases. So this Nitroba case, this is a case that has close to 750 nodes. So these files are serialized into a XML type format, noted here as GML, and then they're deserialized, basically translating the GML back to the data structure. So what you can see here is the 750 node Nitroba case. You can see there's a couple nodes here where there's a significant amount of data being transferred. If you click on a line, you can get some of the node information. So that shows the two different nodes. There's a lot of other nodes out here, and that's because NetworkMiner puts things in like results of DNS searches, and those are all nodes, but they don't actually transfer any data. So it's interesting here, you can zoom in on some of these other cases. One thing you can do is hold down the control key, and if you have a mouse wheel, you can use that as a method to zoom in. And you can see what node this is. And so that's the basic operation of the network graph. I'll do a real quick overview again, and then we can talk about the code. So you have the network graph tab, you have a button that generates the graph, you have some input fields for start and stop time, radio buttons for inside or outside the interval, and a checkbox to enable that capability. The windows have load buttons, different layout algorithms, navigation, controls, and there are 8 currently supported formats that are force-directed, circular, and tree-type layout algorithms. For the packet activity, when you mouse over a node, you see the adjacent nodes, and you see how much data is going to and from those nodes. And each node has a description, data translated from NetworkMiner, has the IP address, has data related to the host. It has the MAC address, the OS detected with an icon representing it, and number of packets that are transmitted and received. You can see in the Nitrova case how those algorithms change the layout of the graph. Now getting into the code. So this was done in Visual 2010. You can see the solution on the right, and there are essentially 6 projects that make up that solution. The first is GraphSharp, so that's a set of graph libraries. GraphSharp demo was a tutorial that I used, and I was able to tailor that for this application and use the theme, essentially graphics theme, present in that tutorial. The NetworkMiner has 4 different projects associated with it. So NetworkMiner namespace here and project is the main app GUI. Network Wrapper is a set of routines for doing live collection and converts it to PCAP, so you can actually do this near real time. Packet Parser is a set of different routines, and it has a lot of data structures, packet protocols, OS fingerprinting, etc. And then the PCAP file handler parses the PCAP file. Looking at the NetworkMiner side of it, you see NetGraph Viewer. So that's a totally new class, about 300 lines, and that processes data from NetworkMiner and translates and communicates it with the GraphSharp side of the house. So you can create graph objects, add vertexes and edges, apply constraints from the GUI. So this is where you would add additional capabilities forensically. And then the next one, the NetworkMiner form, is where you'd put those controls as the inputs. The NetworkMiner form, the network graph has its own tab, so additional forensic features can be added there in terms of providing the inputs for the NetGraph viewer. And network packet had very little changes. It was really just exposing some data like the destination IP and some of the packets and the timestamp. Look at the NetworkMiner form and the button. This is really the first thing that happens when you press the button down. So it does some checking in terms, make sure these fields, in terms of the times that are entered, are valid. It looks at the state of the filtering and determines whether it should pass either between or outside to the routine that will actually be doing the constraint checking. And here it starts to build the graph object. And to do that, what it does is it loops through the main data structure of unique IPs. And it creates node data. So all that metadata that was available for each of the nodes is concatenated and passed over as an ID, and that's what's displayed in each of the nodes. And the OS is converted also, and that is used for some data binding so that you can get the icon and which OS, and it uses 3 different fingerprinting capabilities: Satori, P0F, Ettercap, and it does a voting method to see which OS it thinks it is, and then it adds the graph nodes. The next set of loops, it loops through each of those IP, then it gets into the packets for each of the IP points. And it does a time stamp check to see if it's inside or outside, depending on what you put in as constraints. And if it's valid, it will then increment the node-to-node packet count. Then those node-to-node data structure is looped through, and there we adjust the line thickness using a log function. So this allows you to see sensitivity of 1, 2, 3, or 4 packets, but you're not going to get overwhelmed with a line that's bigger than the boxes if it's 30,000. And it basically adds those connections, that is, edges. And then there's 2 sub-data structures, vertexes, which are nodes. So this was modified to add the OS type. There's also a box color that's been implemented but doesn't currently serialize correctly. And you'll see the ID, OS type, and box color. Those things get binding, data binding to the GUI side of the house. And then edges are connections. You can see we've added line thickness as a property, and the box that comes up that shows the 2 nodes when you check on a line, that is done here with this ID, and then this builds the edges and adds it to the graph. Now the GUI window, the window that comes up with the graph, is coded in conjunction with this main window, XAML. So it's an XML type format, and you can see how the data is bound from C#. So you see binding path ID, so that's that node data, binding OS type, that's where the operating system is determined, and then this is the correct mapping to the icon for it. The main window view model, that provides definition of the layout algorithms and some of the controls. Also has basically the button clicks for load, save, and clear, which are then present here for save graph, load graph, and this is where the serialization, deserialization happens. And most of the testing was done with these 4 projects, which were shown previously. So a small 3-node project from CyberQuest, great for doing quick testing, loading, and checking. There's a medium node case, some banking traffic, had a lot of host data, etc. And then a couple larger projects. This challenge case of a honeypot exploit had 450 nodes. And then the Nitroba case, it had about 750 nodes. Interesting thing about this is you see a lot of the ad trackers and other things show up in this.